Today we're looking at a bacteria exponential growth model. We're told that researchers recorded that a certain bacteria population grew from 100 to 500 in 6 hours by an exponential model. And then we're asked, at this rate of growth, how many bacteria will there be 24 hours from the start of the experiment? So let's go ahead and what formula are we using if it's bacterial growth by an exponential model? Well, we're going to use A equals A naught. So the ending number of bacteria is going to equal the original number of bacteria times E to the KT, where we're looking at K being the constant rate of growth and T being the amount of time, in this case in hours. So the first thing we need to figure out is, well, let's go ahead and identify our parts first. So A, what do we end with? That equals A equals 500. A naught is what we started with, which was 100. E is just the transcendental number. K we don't know, but we do know that, so K equals question mark, T equals originally 6 hours. So here's the key, is that first we need to solve for K in this formula, in this equation, substitute and then solve for K, and then we can apply the 24-hour time period. So first off, let's go ahead and substitute into A equals A naught times E to the KT. Well, we're going to go ahead and switch sides. A naught is 100, so we end up with 100 to times E to the KT. We don't know what K is. 6 is T, so E to the 6K equals our ending amount, which is 500. Divide both sides by 500. We get E to the 6K, or divide both sides by 100 rather. E to the 6K equals 500 divided by 100 is 5. Take the natural log of both sides, and then use the power property. 6K times the ln of E, the natural log of E, but the natural log of E is just 1. So 6K equals the natural log of 5. So K equals the natural log of 5 divided by 6. So now we have what K is. We want to keep that exact, by the way. We don't want to take a decimal approximation. And now A naught, we're starting with 100. The only difference is that now we're going to have our K, and we're going to be looking for the ending amount. So we have A naught is 100 times E to the K is ln of 5, natural log of 5 divided by 6 times T. Well, we're given now 24 hours. So this is times 24. And that's the ending amount that we're looking for. So this ends up being, if we simplify, 24 divided by 6 is just 4. So this is 4 ln of 5. So this ends up 100 times E to the 4 ln of 5. Well, now we can take this to the front using the power property, the 4 to the front. That equals 100 times E to the ln of 5. Go ahead and go back here. Ln of 5 to the 4th. We're actually not using the power property. I'm just moving where that exponent is. We're taking an exponent to an exponent when we multiply, so I'm taking the 4 outside for the product, 4 ln of 5, and that's because e to the ln of 5, so e log base e of 5, we know is just 5, so this ends up being 100 times 5 to the 4th. Well, 5 to the 4th is 625, so 100 times 625 means that after 24 hours, we would expect there to be 62,500 bacteria. So using the given information, we found the constant rate of growth, K. We substituted that back into the formula with the time period that we're looking for, 24 hours, and then solved by simplifying 100e to the ln of 5 over 6 times 24 simplifies eventually to 100 times 625, or 62,500 bacteria after 24 hours.